Hello, I'm Nima Zanjani, and my presentation is on what I did in my Rokos internship on designing thermoelectric devices. But first I should explain why we study thermoelectricity. As we all know, climate change is a deeply important and existential issue for everyone. We all feel this in our generation especially. It's terrifying. And that, along with the global energy crisis and the rise in AI hype, means that, especially due to needing more AI data centers and needing more, which requires a huge amount of water to reduce the waste heat, it's a huge issue and is very worrying. Thermoelectricity has a potential to reduce some of these issues by being able to turn heat into electricity or voltage that you could then drive the circuit with. Drive a circuit with, which in this case could potentially be used to put back into the original circuit, improving the efficiency considerably. The task of the internship was therefore to figure out how to create a practical device that could work for these systems. But first I should explain how thermoelectricity works physically. To start with, we should think of a metal at 0 degrees Kelvin. You can think of the bar chart in the top left as a stack of electrons increasing in energy. However, it's more interesting at higher temperatures. At higher temperatures, this straight line that you see at the top smudges, which means that some of the electrons get a higher amount of energy, which means that there's a slight gap below. Looking in the bottom left diagram, this smudging is related to the temperature, so more smudging when it's higher temperature. So if you put a hot object next to a cold object, the higher energy electrons will want to reduce their energy, moving to the cold metal, which that movement is a current, which we can use to drive a circuit. The amount of current produced is controlled by the Seebeck coefficient, which is about a millivolt per Kelvin, which is pretty low and is not really able to drive circuits very well. But the idea is if you get a lot of these devices in series, you could actually get a proper voltage that you could drive a circuit with. But how do we create one? So one of the most feasible methods for this is molecular electronics, which is the idea of effectively building a circuit based around a central molecule, which you then attach the rest of the circuit to. The first two methods work largely by effectively creating a very small crack in the circuit and getting the molecule to fill that gap, which then you're able to use the properties of that molecule in the circuit for its properties. The first way of this is by constructing the circuit on a flexible material, flexing it, and then you create a very small crack in between two bits of metal. Electronic brake works similarly, except you drive a large current through, which creates a very small crack. But the one the semiconductor group at Cambridge uses, effectively you get a layer of gold, which you then create self-assembled monolayers, or SAM, onto, which is effectively growing hairs out of the gold, such that the molecules point out. And then you can wrap that in graphene, which acts as the other junction to point to the rest of the circuit. This method, compared to the other two, is scalable, which you could actually make a lot of devices with this, and uses optical lithography, which is a well-known manufacturing process which is used in semiconductor manufacturing globally. But what do we do? So we decided to do the third method, as we were very familiar with it in the fabrication and design, and we also had a design that worked for this. However, though we know it has good properties, we haven't actually been able to test practically how much voltage we can get for a given temperature difference. And therefore, my task was to research and model the flow, along with attending design meetings with Professor Ford and two PhD students, Chunyang Miao and Jahi Li. The first way I was simulating this was through modeling the entire device as a thermal circuit, which is effectively you imagine the whole device as being a flow of different resistors, which instead of flowing current, you flow heat. And in doing so, you're able to examine which parts you want to be resistive, which parts you want to be conductive, and vary the parameters for it to work. This revealed that the SAM needed to be much more resistive than we originally thought, and also made us realize that the geometry of the device had to be had to be adjusted a lot to get it to work properly. We then moved on to modeling the device in COMSOL multiphysics, which uses a computer-aided design method. Computer-aided design, or CAD, is a typical engineering type of software, but the difference with COMSOL is it has a very sophisticated physical modeling system, which is very good for modeling flows, including electricity, but especially heat, which is what we used it for. But in doing so, we realized that the graphene was not cutting it. We needed to, it did not provide the necessary heat flow to get to the junction. And so we decided, so we figured out that we could potentially etch under, as in dig a hole under the graphene to create an air gap, which is more thermally resistive than the material that it was originally under, along with creating, using, instead of a single layer of graphene, many of them, about 6 of them, to ensure a more proper heat flow. This led, along with many other optimizations, led to the final design in the top left. This whole design is about 2 millimeters across. The zoomed in picture in the top right is much smaller. It's about 100th of that. One of the most fun things about the internship was getting the previous design and scrolling in and just seeing how detailed it got as it went in, but also how small the actual functional part of the device is. But we were also able, in design meetings, able to figure out that we could potentially put a bunch of these junctions in series, which could actually get a macroscale voltage. The other research times before has been with a single junction, but this could potentially get an actual macroscale voltage reading. The picture on the bottom is about 100 of these junctions in series, so you could actually get a large voltage from this. But now that we had the design, the next steps are to begin fabrication and to move on to testing, which I sadly ran out of time for and is being handed off to Chengyang Miao, the PhD student I was working with. But if this provides promising results, this would be a big step in the direction of creating actual functional devices that is not only works, but is scalable. We could actually make a lot of these at once, which, as I've explained, would be very great for climate change and all environmental stuff, but also has applications for anywhere you have waste heat. So including potentially charging your phone with a waste body heat from you, which is very cool. Yeah, thank you very much.